Um, Today I would like to talk about another pair of quantities which link interaction with motion. And well, as in the past, if you look at various versions of work energy theorem, various versions of Newton's second law, it is more or less convenient to use these laws in particular circumstances. Well, these quantities are also useful in particular circumstances. Although, in principle, if you really want to suffer, you can analyze a free fall using concept of angular momentum. And if I have time, I will do this today. Well, these quantities are particularly useful for analyzing objects of pieces of machinery which rotate, although it isn't limited only to those. But from the engineering point of view, whatever is rotating, this will be the best way to think about it. First, I will introduce a quantity which describes motion. This quantity is angular momentum. Now, I noticed that in the lab you already were playing with angular momentum. However, you were precisely playing with what angular momentum? Of what? Of a circle, of a disk, right? Now I'm introducing it for a particle. Now, particle cannot rotate. Angular momentum, I mean, we'll see what later on how angular momentum is of individual particles is related to angular momentum of an object. So, if a particle has a certain momentum p, angular momentum is defined as the product of position of the particle and momentum. I use small letter L to indicate that it is for a particle. So this is definition of angular momentum of a particle. Now, what kind of multiplication are we using here? Yes, Chris? No. Vector product. And the result of vector product is what? A vector, correct. Result of what product of two vectors is a number? Dot product. Do we have a product which involves a number and results in a vector? Vector times number, correct. Product of a vector and number results. How many products do we know? Or at least we're supposed to know. 4, correct. Please, I mean, we are already learning how to multiply for 2 months, and we are still confused how to multiply. All right. Because probably let's say that if I want you now to tell me what will be the, how about think about me, that I am a particle, okay, and I will be walking that way, which means that my momentum is also that way, right? Show me what is my angular momentum. Now, angular momentum is always about a reference point. Without reference point, we cannot have angular momentum. So consider yourself as the reference for angular momentum. And from now on, actually, I don't want you to speak just angular momentum. Angular momentum is too vague. You have to say always angular momentum about what? So right now, I want you to identify the direction of my angular momentum about each of you. Show me the direction of that angular momentum if I walk that way. All of you, consult with your neighbor. Okay, a lot of you are showing that this is the direction of angular momentum. It's incorrect. This is the direction of momentum. Now, which way? This way? That way? How do we get it? You forgot again how to multiply using vector product. Yeah, so if I have, let's say, vector A and vector B, we use right-hand rule. Mark is right. We use right-hand rule. The way I do it, first I align my right hand with the first vector. So this was vector A. I will align it that way. So how about if I take it there? First vector is R, so I have to align it with vector R. Well, how about if I take it actually from somebody else? How about from you, right? So if I take it from her, this will be vector R, right? Now I have to rotate my hand in such a way that I can bend those fingers in the direction of the second factor. So the second factor was my momentum. And then, if I'm able to do it, the thumb shows the direction of angular momentum. So if I walk that way, my angular momentum is down. My angular momentum about each of you. Now I change the direction of my motion. What is the direction of my angular momentum now? About you? Up, correct. All right. Yeah, so we use right-hand rule to determine the direction of angular momentum. I hope that you got it. All right, because now the corresponding description of interaction is called torque. And torque is defined in a very similar way. That if a certain force is exerted on a particle, then torque due to this interaction is equal to the torque about the same point, about the reference point, is equal to the vector product of position of the particle multiplied by the force. All right, so now I want each of you to show me the direction of the gravitational torque about you. My gravitational torque about you. Consult with your neighbor. What is the direction of my gravitational torque about you? Which way, Chris? Down? Okay, so Chris, can you get up and show everybody how you do that? Yes. So let's see. What is the direction now of the position of my position? Well, I mean toward me. Yeah, from you toward me. I'm not up there, right? It's toward me. So vector R is from Chris to me. All right. Now gravitational force is down. Very good. Yeah. So now twist your hand in such a way that you can, now you can bend it, and the thumb shows the direction of the gravitational torque. So which way is the gravitational torque? That way. A gravitational torque is that way. I know that it is confusing because it violates somehow your intuition. Now it is that it's almost like, well, I walk that way and I say that this is the direction of my motion, right? This is what I'm saying. However, this is the simplest way. I'm sorry. For acceleration velocity, it was more intuitive. Because indeed, for velocity, the direction of velocity is consistent with the direction of the motion. However, for acceleration, it isn't true. Right? Because, for example, if I walk that way, what is the direction of my acceleration? Yeah, perpendicular to that. I was moving along a circle, so acceleration was that way. So it's okay. I mean, we had already quantities which are associated with motion, which are perpendicular to the direction of the motion. Now, that one on top of it says that, that the direction of the motion is like that. All right. So using right hand, we use right hand rule again to determine the direction of the product. What product do we have here? Vector product. And in vector product, what do we multiply and what do we get? Vector times vector, and we get a vector, correct. Now, do you remember how to find magnitude of a vector, of a vector product? Right, not absolute value, then it's magnitude of, yeah, so if I have vector A and multiply by vector B, let's say the result is vector C. So magnitude of this product is equal to magnitude of the first vector times magnitude of the second vector times, not the, what function, yeah, angle between them. Which one? Not, that is scalar product. Scale, and this is not a magnitude, but just scalar product takes cosine of the angle. Vector product requires sine of the angle times sine of the angle between the two vectors. Now, somebody got confused with this expression. What do we get when we calculate this? Scalar product. Should I write it like that? Is this a symbol for scalar product of vectors A and B? No. I will have to put arrows over there. Now see the difference actually between the major difference between this formula and this formula. When we use this formula, what are we getting? Scalar product of two vectors, A and B. If I use this formula, what am I going to get? Magnitude of the vector product, not the vector product. Vector product is C. This formula just says what is the magnitude of the vector product. Now I brought it over here because let's say I have two vectors, let's say A and B. So angle alpha is over here. When I'm interested in the magnitude of the vector product, well, I can always look at that, yeah, because now, what is? I mean, where I would have to mark B. Oh well, how about if I write first expression for magnitude of vector product? Magnitude of A times magnitude of B times sine of angle between them. Now, on arrows, you remember that magnitude is related to the length, right? So really, if you look at A for an arrow, it's the length of this arrow, right? Now, this is length of this arrow. All right. If I multiply B by, in other words, length of this arrow by sine of that angle, what am I going to get? I'm not going to get length of B. They are completely independent. Well, I'll show you what I'm going to get. We say? The distance between B and A? Nope. Well, we have to imagine a right triangle. Now, length of this multiplied by sine of this angle will give me this length. Do you see that? In other words, if I combine it that way, really this product is the component of vector B perpendicular to vector A. Yeah, this component, do you understand me? Now, I can also associate it a different way. I can write down actually that this is B times A times sine alpha. And think about that. Very good. So now I have to A times sine alpha gives me this length. So it is component of vector A perpendicular to vector B. And so, for example, now, if I, how about if we think now about various torques? Let's say that I push it down with a force of 1 Newton. What is, I mean, let's say this is 1 meter. This is a meter stick. What is the magnitude of the torque which I exert, torque about this point which I exert? This is 1 meter. And I'm pushing downward with the force of 1 Newton. It will be 1 Newton meter. Correct. But it will be 1, yeah, because it is 1 times 1, and this is already perpendicular. I can think about sine of 90 degrees, right? All right. Now, how about I will arrange it that way, and now I'm pushing it downward with the force of 1 Newton. Downwards. What's the torque? Zero. Who said 0? Yeah, why did you say 0 now? Yeah, the sign is now, it will be sine of, well, position vector is that way, force is that way, so it will be sine of 180 degrees. So it is going to be 0. Now, I'm sorry that I erased it, but with the trick which with this geometrical arrangement which I just erased, what you really have to think of when you analyze the torque is to see a component of the force, a component of my force which is perpendicular to the stick. Now if I push it down, what is the value of the component of the force perpendicular to the stick? 0. Yeah, I don't have a component sideways. And only that sideways components contributes to the torque. Do you understand me? So, for example, now if I, well, how about if I do it like that? So over here it is 45 degrees, and I'm pushing it downward again with 1 Newton. What is the magnitude of the torque? Why don't I make a drawing for it? So magnitude of the torque about this end when I'm applying here a force of 1 Newton. Well, directly we could calculate that it is 1 meter times 1 Newton times sine of the angle between these two vectors. Well, these two vectors make an angle of 135 degrees. Right, so it is square root of 2 by 2. So it will be square root of 2 by 2 newtons. This is if I calculate it directly from the definition. Now I could do it that in such a way that, well, why don't I just concentrate first on the component perpendicular to the stick? So if this force is 1 Newton, what is component perpendicular to the stick? This component, how strong is this, how big is this component? Square root of 2 over 2 newtons, 0.7 newtons. All right, so that way, now I will have that this is 1 meter times square root of 2 over 2, 1 meter, square over 2 of 2 newtons, and now I have sine of component is already perpendicular, so 90 degrees, which is 1, so I never think about it even. I just take the component. So I'm getting that the torque is square root of 2 over 2 Newton meters. It's the same as before, right? Now, I can also do it the third way, and rather than taking component of force perpendicular to that position vector, I can take component of the position vector along perpendicular to the direction of the force. Actually, that line is referred to as the line of force, and then, well, where is it? It's over here, the component perpendicular. Now, how long is that one? If this one is 1 meter. About 70 centimeters, right? It is square root of 2 over 2 meters. So this time I will have square root of 2 over 2 meters times, now this time 1 Newton, times, and again it's sine of 90 degrees, which I usually don't bother. So we get the torque is square root of 2 over 2 Newton meters. This distance, by the way, has even a name. It is called a lever arm. This line is a line of force. This one is lever arm. Well, lever arm really results from magnitude of that position vector multiplied by sine of the angle between the two vectors. All right. Now we have a description of motion. We have a description of interaction. Newton's second law relates them. For particle, therefore we can derive fifth version of Newton's second law. It is for angular momentum of a particle. However, you will never use this version of Newton's second law for particles. Doesn't make sense. It's better to use the regular one. However, formally, let's now take a look at what rate angular momentum is changing. So, and help me, as usually, with the derivation, because I'm very bad with where do I get everything from. So where do I get this from? Instead of angular momentum of a particle about the reference point, I wrote that this is position of the particle with respect to that reference point multiplied by momentum of the particle. Why? From the definition of angular momentum of a particle about a point. Where did I get this from? It's a product rule, correct. It's a mathematical step. Derivative of a product is is a sum of products, appropriate products. Now, remember that vector product is not commutative. It does matter in which order you multiply the factors. Therefore, and that one works. So you cannot, if you learned product rule that it's derivative of the first function times the second function plus the derivative of the second function multiplied by the first function, then it's wrong. Derivative has to be one time, in one term it has to be first factor, and in the second one it has to be second factor, the same order as in the product. All right, help me with that one. It's a difficult step. Let me give you a hint. This term is 0, always. Let me give you another hint. What is dr over r? No. dr over r is a rate of change in position. What do we call it? Velocity, correct. So this term represents velocity of the particle. Now, what is momentum of a particle? How is it defined? Mass times velocity. What's the angle, therefore, between these two factors? 0, correct? Because here we multiply velocity with velocity multiplied by a number. Both vectors are in the same direction. What's the vector product of two vectors which are in the same direction? Prove it to me that it's 0. Sine of the angle is 0, correct. So it will be magnitude of velocity. Well, in other words, speed. Speed times magnitude of momentum times sine of 0 degrees will give me 0, and this is the magnitude of that product. Well, what vector has magnitude 0? Only one vector has magnitude 0. It's the 0 vector, correct. So therefore, this term is 0. All right, now help me with that. It's not the definition of net force. It's what? Newton's second law. Which version? You have to be good in that to recognize which version is which. Christina? The second one, right? In an inertial reference frame, rate of change in momentum of a particle is proportional to the net force exerted on that particle. Correct. So here is the net force exerted on that particle. I will write it that way. Where did I get this from? Definition of torque. Yeah. So in summary, in an inertial reference frame, the net torque exerted on a particle is equal to the rate of change of its angular momentum. So the derivative of angular momentum of a particle with respect to time is equal to the net torque. Where did I use the fact that it's an inertial reference frame? Where inertiality of the reference frame is required in that derivation of that proof? Yeah, because I mean, really, this is the proof of that theorem. Fifth version of Newton's second law is a theorem which is derived from an axiom, Newton's second law, first version. So where did I use fact of inertiality? Nope, not here. Not that this product is 0. Here? Right here? Right here, correct. Over here, I use the fact that it has to be in an inertial reference frame. How can you see this? Because I use Newton's second law, second version of Newton's second law, which requires inertiality of the reference frame. All right. So for at the end, now I will want you to see, to figure out what is acceleration of an object if I release it using this version of Newton's second law. So here I have a ball. Well, there's a gravitational force exerted on it. I will choose this reference point over here. This is a reference point. And let's say that this distance over here is r. So if this particle moves has velocity v, what is angular momentum of this particle? Yes, I can write down that this is r times v. No, sorry, angular momentum. I wanted angular momentum times mv. Right, this is, well, you know, why don't we come back to this problem tomorrow? This will be the end of the lecture, and see you tomorrow.